My friend runs up some stairs. He's 100 kg. And the total distance is 20 meters, and he gains 5 meters of height. I want to know the power output. So for sure, I'm going to recognize that power is equal to the work over time. And I might say that work is force times distance, but I'm going to have a real hard time finding the force because there's acceleration and there's gravity. So I'm going to use change in energy over change in time. Because I know that at the beginning, his energy is 0 because he's not moving in the beginning. And at the end, he has potential energy, so change in energy is equal to this energy, gravitational potential energy, plus the kinetic energy. Because he's gaining potential energy, and he's still going strong at the end, so he has kinetic energy as well. And so this is mgh, or mg delta h, plus 1/2 mv squared. I forgot to say why I can use an energy lens. It might be worth noting what the energy transition is. Many people said potential energy is changed to kinetic energy. Now, this isn't true. These aren't equal. This would be true if we started with potential energy and fell off the cliff because there'd be no work being done. What we want to recognize is that my friend's work turns into potential energy and kinetic energy. Okay, where did that come from? Yes, we could say it comes from the ATP in his body or the food that he ate, but we're not really concerned with that. We just want to know what energy output did he give us. So we go straight to this part. Now we calculate this change of energy, which is 100 kilograms times 10 meters per second squared times 5 meters plus 1/2 times 100 kilograms times, the speed. I'm going to use some kinematics because I know the distance and time. So speed is change in distance over change in time. I could write kinematics here is 20 meters divided by 4 seconds is 5 meters per second. So I have 5 meters per second. Don't forget to square it. So I end up with 5,000 kilogram meters squared per second squared, plus this is 25 times 1/2 is 12.5 times 100 is 1250 kilogram meter squared per second squared, which is equal to 6250 joules. Now it's worth mentioning this is a slight underestimate. Why? Because here we found his velocity, delta x over delta t, is the average velocity. But that's not the same as his final velocity. In fact, we know his final velocity must be slightly greater because v0 was 0. Now it's not true that you have uniform acceleration. If that was the case, his final velocity would be 10 meters per second, which is the fastest a human can run. But we know when we run up some stairs, we initially accelerate a whole bunch. And then we run pretty much at a constant speed. So the velocity is pretty close to 5 meters per second, a little bit larger. So maybe the kinetic energy is a little bit higher than we calculate. In any case, power is equal to this change in energy over change in time, which we find is about 1.6 kilowatts. The order of 2 horsepower. Quite a bit.